invitation for today's seminar. It's really a pleasure to be here.
You're welcome, my pleasure.
Thanks everyone also for attending as well. So what I'll be talking about today is, one of these initiatives we've been doing at the interface of optimization and machine learning, and that's actually joint work with one of my PhD students, Shubair Amirnikia, and a colleague of mine, Hubert Pun. What I'll be talking about, new models that we're introducing for consumer preference learning. So consumer preferences, I mean, it's not surprising for anyone nowadays that there is a lot of consumer learning when it comes to the behaviors of consumers and retailers trying to learn how people behave when they are shopping. So we actually no longer get surprised when we're just going to Amazon and seeing some of products being shown to us, sort of promoting or pushing us to do some impulse buying. So nowadays, this is quite mainstream. So no one gets surprised by when they learn about, when they know that manufacturers, retailers, or everyone in the supply chain is trying to learn how they behave so that they can design their products better or promote their products or try to push consumers to do impulse buying. Probably one of the main things that is used where consumer preference is used, it's more than just pushing consumers to buy more products through impulse buying. It's really about more strategic decisions that happen in terms of designing a product and selling a product to a consumer. So although no one gets surprised about being in a position where they are pushed to do an impulse buy just because they learn a retailer learned their behavior, probably the newer things are that these preference learning, that they really drive the pricing strategy of a product. They really drive the design of a product. They really determine how the product is delivered to the market. For instance, if we look at bank loan interest rates, like these are targeted through a profiling of consumers who the bank loan is being sold to. So it's really about learning how this consumer will react to an interest rate, for example, and devising this strategy to deliver a bank loan to them. Or they could, for instance, it's very common to use this preference learning to help shape the design of the product. For instance, like in the vehicle, in the auto manufacturing industry, it's quite common that we see different versions of the cars being offered in different markets. For instance, there is a big difference, for instance, with the Volkswagen Tiguan that is sold in North America, which has a much longer wheelbase, for instance, to the one compared to Europe. And that's just driven by what the market appreciates and what the market likes to buy in different regions or different consumers. Another thing, for instance, it's what products are delivered or what products are or what services are offered to a market. For instance, certain products are not offered in certain markets while they are offered in other markets. For instance, the smart car is discontinued in the USA and I think the North American market because, I mean, no one likes to buy these tiny small cars in that market. However, they are very common in Europe. And these are all based on learning how the consumers react to a product and what product they would buy through certain learning of the consumer behaviors. Probably one of the most interesting examples for me in that space is sort of this bold move by Apple when they removed the headphone jack from the iPhone. And that was really removed not because, I mean, of course there is a lot of talk about this sort of old feature that is the headphone jack that doesn't serve anyone, no longer serves sort of the requirements in terms of quality and all of that. But on top of this, it's really one of the main things that drove that decision to remove it is really to accommodate other features that would go in the space of the headphone jack and all the electronics that are required to accommodate that. And that's really because the consumers, well, at that point in time, started appreciating other features. For instance, a second speaker that could deliver a better quality voice in the iPhone, or the Taptic engine for vibrating. And consumers started appreciating these features. However, of course, there is no space to pack all of these features that consumers appreciate in this very tiny rectangular, let's say, rectangular phone. So something has to go out of this. So what do we take out from this? It's really, we take out the features that the consumers would appreciate less, or sort of the features that would drive, would be less impacting the sales, and putting features that would impact the sales more. So that's just one of the, I think, quite an interesting example how a preference learning model could help out making a bold decision to take out a feature that from a product, that a feature that consumers are very used to, and putting features that consumers actually appreciate, but really very few would be willing to take that bold move. Now preference learning, as I mentioned already a few times, it's really has become mainstream. I mean, before, probably most of the data that we would generate about consumer behaviors would come from focus groups or small selected markets to collect data. But nowadays, like with e-commerce, we have global markets, very diverse markets, where data can be collected from. So doing preference learning has become a whole lot easier, of course, with the growth of ML and AI. So this has become a lot more mainstream. But also from a retail perspective and the consumer perspective, there is a lot more expansion of the content. So we no longer have a single version of a product. We have many versions of the product. And that's really mainly driven because we need to accommodate personalization, and that's really to drive profits. So there is, of course, from a technology perspective, and the availability of the data has enabled us to do preference learning in a more mainstream way, but also there is a lot to do with driving profits, and driving profits through product personalization and content personalization, which requires to accurately learn consumer preferences. And besides sort of this idea of accurately learning consumer preferences, that's nothing new. So that's like, it's been like over 40, 50 years where there has been work on preference learning and models for preference learning. Probably what is newer in the last few years is something to do with more privacy preserving methods. So it's not only that we need to learn consumer preferences, but consumers have been are becoming a lot more conscious about their privacy and their and how their data is being used. So we'd like to accommodate the privacy preserving aspect of all these methods, but at the same time we need to keep the robustness and the accuracy of the models that we're creating. That's really what has what is the main title of that has driven that research, is the robustness of the models that we'd like to create, and at the same time looking at the privacy aspect of the models. And as I present the details, I will highlight these aspects when I'm presenting the details of the model. And there is, of course, there is a lot in terms of the market for preference learning. I mean, there are tons of companies looking at marketing and offering software and technology to do preference learning. So that's really at a very global scale. So what is a preference learning model? So the main thing is we would like to create a model that offers us an understanding about the relationship of a market mix decision. And what I mean by market mix decision is what products are offered to a consumer and how that leads to a consumer purchasing the product or the service itself. Sort of that's the main thing in sort of capturing in these models. So it's not that just consumers just buy products. They need a product and they go out and buy it. There is more to it than this. So the decision of a consumer to purchase a product is really by looking at what is offered to them. So, and it could be a single product, but this product has many features. And what are all these combination of features, and what does it lead in terms of a purchase decision? So as an example for this, so let's say, we're offering a smartphone, for instance. A consumer is truly okay, so they need to purchase a smartphone. But when it comes to purchase decision, so which smartphone do they actually purchase? So let's take an example of the iPhone. So when a consumer looks at an iPhone, they are not just looking at an iPhone. So what they are looking at is basically a collection of features, which is a camera, a high-end camera, let's say 40 megapixel camera. On top of this, they are purchasing a product that has a 6-inch screen. So that's the second feature. It maybe have a 16 gigabyte of RAM. That's the third feature. So it's the cumulative of all these features that drive to the consumer to decide, yes, I'm going to purchase that product, or no, I'm not going to purchase a product. So when I look at the market mix, it's really the different variations of the iPhones that are being offered at that point in the market. So one could have a 40 megapixel camera, another one could have a 20 megapixel camera. One can have a 16 gigabyte RAM, another one could have an 8 gigabyte RAM. And all these combinations come together to form a product, and you could have 4 or 5 different variations. And at the end of the day, the consumer will pick one out of all these variations. So I would like to create a model that would tell me, given a certain variation of a product, would the consumer buy it or not? And there is more to this. So when you create such a model, so it's not only that it will tell you if a consumer will buy a product or not, but it really will tell you, well, what features are driving that purchase decision. And when you know what features are driving that purchase decision, that helps you out actually design the product itself. So when I'm looking at a preference learning model, so I know what consumers are, what is driving the consumer decision to purchase. So when it comes to the next version of the product, well, what should I update to improve that chances of the purchase? What should I be upgrading my camera? Should I be upgrading my memory? Should I changing my screen features? So such a model would drive the decision of product upgrades, and what changes and product features would drive the willingness to purchase eventually. Besides this, besides sort of driving product upgrades, so it helps us differentiate the consumer markets. It helps us segment the markets itself, because although we're offering, so we're aggregating certain parts of the markets, but all the markets don't. And as I sort of, one of the main cores of this work is that the markets are not uniform. So the markets, different regions have different preferences. So it helps us segment. It helps us sort of drive product features, product upgrades for different markets differently, and this will help us grow profits. And the whole theory about this preference learning is really based on utility maximization. By this, we mean like a consumer will purchase a certain product only if that utility of that product will exceed the reservation value. So I'm looking at a product, I will only purchase it if the utility of that product meets a certain minimum threshold. I'm not going to purchase the product otherwise. And the other assumption that we make there is that when I'm comparing two products or two different versions of a product, and that's probably more accurate to say, I'm comparing two different versions of the iPhone, I'm going to purchase the one that provides me with the higher utility as a consumer. And there is this, I'm going to make this assumption that this is strictly enforced. So I purchase product J over product I if the utility of product J exceeds the utility of product I. If, of course, when I'm looking at a collection of products or a market mix, as I said earlier, I'm going to purchase the product if it exceeds the reservation price. So there is the choice of not purchasing anything. So if none of the products meet this reservation price, I can have the decision of not choosing anything. Besides these assumptions about sort of the utility maximization of how that drives the consumer behavior, we have also very strong assumptions about the different substitutes or the different variations of the products. We will make the assumption, or all these models make the assumption, that we have perfect substitutes. So when I'm looking at M alternatives, or M different variations of a certain product, or M different variations of the iPhone, I will choose only one of them. So I'm going to make a purchase one single product, and sort of I'm indifferent in terms of these products, as the sense that they all exceed my reservation utility, a minimum utility threshold. So anyone that exceeds this utility threshold is good to me. I'm just going to choose one that has the highest utility among all of them. Also, when we purchase products, there is always repeat purchase of the product. So today I purchase a smartphone. In a year or two, I'm going to purchase another smartphone. However, the idea of variety doesn't play in that mix. I'm strictly purchasing the product based on utility. I'm not really seeking to have different variety. I'm not seeking to have different versions of a product that I'm purchasing. So I have a certain car today. I mean, I don't get bored of that brand. I try to choose a different brand just because I'm getting bored. It's simply based on the features of the product itself where I'm making that purchase decision. The last assumption that I will make, which is not really restrictive in terms of the model itself, is that I'm assuming all the prices are the same, so unitary price. If this is not the case, I can sort of instead of talking about utility, we can talk about marginal utility, which is just the utility divided by the price. But just for simplicity of sort of the notation, we assume that the prices are the same for all these different variations. In that sense, I'm just talking about marginal utility. Any questions for me, by the way? So feel free to interrupt me if you'd like me to address any questions. Okay, so I'll be making these assumptions for creating the model, and that's not really assumptions that are only hold for what I'm presenting today or the models that we've created. These are the common assumptions that when it comes to a large majority of the preference learning models that we see in the literature. And there has been, as I said, this is not really new, so there has been a lot of work on preference learning going back to sort of the 70s, the earlier work of McFadden authors in 1973. There has been since then a lot of work on this, looking at different machine learning type models to learn a consumer utility function. The type of models that we're presenting are extensions of the support vector machines models, first presented in the literature by F.G. New in 2005, and Couey and Curry in 2005 as well. So sort of there has been a list of publications on using support vector machines types models to do preference learning, and these have been the most common over the last few years, both in terms of research literature and as well practical methods for different features that I'll be talking about in a second. With that being said, so there has been, if we look at the literature, there has been less interest in looking at more complex models than, for instance, logistic regression or support vector machine, just simply because there is a lot more interest into explainability and simplicity of the models, mostly because they drive marketing decisions, they drive investment decisions. So there is a lot of business context that comes to these models. So there is a lot of interest in looking at explainability and a bit of simplicity in terms of what could be a more complex black box models that sort of do predictions, but provide less explainability. So in terms of these types of support vector machine models, so there are some assumptions about sort of how the data is generated and how the data is made available so that we can create these models. So sort of the assumptions that are made in terms of the data is that we have t-choice occasions. So we're going to look at as a start, we're going to look at a single consumer, and that consumer is choosing a product at discrete points in time, and we have these t-choice occasions. At each point in time, they're going to look at k alternatives. So they have k products that are offered to them. So there are t-choice occasions. At each occasions, there are k alternatives that are offered to them. Each alternative is actually a vector of attributes. So these are the features of the products. So we have a vector for each product. It is a vector of size j that gives us the features of the product. So feature number 1, for instance, is the quality of the camera. Feature number 2 is the size of the screen. Feature number 3 is the quality of the screen. Feature number 4 is the quality of the voice. Okay, so it's a vector of different attributes, or a vector of different features. And each vector is the description of the product itself. Then we have the consumer utility, and that's really what we're trying to learn. So basically, the consumer utility is a utility function that gives us a weight for that particular feature. So it's a vector of size j, similar size as the size of the features, and gives us a valuation, the consumer's valuation for that particular feature or for that particular attribute. So of course, so the higher this value for W, so the more it indicates that the consumer values this feature more than another feature. So basically, the consumer's utility of a product is just the dot product of this W, which is the consumer's utility vector multiplied by the features of the product. So without loss of generality, I'm going to assume the consumer is shown k alternatives. They will always pick choice number 1. Just because it simplifies the notation, but of course, in reality, they don't pick product number 1, but the order of the items could be sorted so that the consumer pick always item number 1. Okay, so just because it simplifies the notation. So to this end, the other set of assumptions that we're making is that this consumer utility function is just a linear utility function, and it's a linear in terms of the features of the products. So when I'm talking about the product again, I'm not talking about the product itself anymore. I'm talking about the collection of features. There is a weight for each of these features, and the sum of all these weights multiplied by the values of these features gives me this utility that I'm trying to maximize. Besides this, so we have a single utility function that we're trying to learn. So all sort of this data that is coming from either a single consumer or a set of consumers that are uniform. They all have the same utility function. So we're just aggregating all their past choices. And as I said, it's just a linear function that is of the product qualities. And these are not new assumptions, these are pretty uniform across the literature. In terms of applicability of this data generation, so sort of data availability, and you can think of it as, again, you're trying to buy a product from Amazon, and then you type the name of the product, and then you get a set shown to you. So you have, I don't know, 10 products shown to you after you search on Amazon, and you pick one of them and you purchase it. So that's just one input data that we have available to us. So that's basically the choice-based conjoint analysis that is offered. So you've just offered a set of products, you pick one, and that's really driven by consumer behavior. And you can see by this sort of why these types of models have become very mainstream in the industry, because that's really how the industry functions. You always look at different set of products and you're always picking one. So the data is readily available nowadays, compared to looking at focus groups where you show them products and they pick one, and then there is a lot of uncertainty in there. So that drives the decisions. As I said, so always alternative one is being picked up. So in terms of how the model will look like, so we have this constraint that says, well, the utility of product number one, so the dot product of x1t at choice occasion t multiplied by this utility vector exceeds the utility of the rest of the products, all the products that you didn't pick. So that's a constraint that we have in the optimization model. Well, it's quite unlikely to have fit all these constraints. So probably now you are seeing where this support vector machine idea comes in. So it's quite unlikely to have this constraint strictly enforced for a linear function. So we really would like to introduce a slag that allows us to have some errors in the data. So we cannot really meet all these constraints. So we have some slags or some errors that we can introduce. Minimizing the error or finding a function that minimizes all these errors leads to overfitting. So that's sort of what the main driver for the support vector machine models. So we don't really want to only minimize these errors, but rather sort of look at a function that gives us the biggest margin among all these different constraints. So that's the support vector machine model. So sort of the main difference in here is that we're comparing a alternative one to the other products. So in fact, when a consumer looks at all these products that are available to them, they are not looking at product one and making a decision, should I purchase it or not? And then looking at product two, they decide purchasing product two or not. They are not really doing this. They are actually doing a comparison between product one and two, product one and three, then product two and three. They are doing a comparison between these two products. And then when they compare product one and two, do I purchase one or two? So in fact, so as a consumer, when you are looking at the different choices that are available to you, you're not looking at strictly at one of the choices on its own and making that decision. You are looking at the difference between these two choices that are available to you and making that decision. So in fact, the data that is available to you when we look at the feature, so we're looking at the feature of differences between two different products. So for instance, when we're picking between product one and K, I don't look at making the decision for product one, then product K. I look at the difference between one and K, and I say, well, do I prefer one or do I prefer K? Of course, if I look at product one and K and say I purchase one, the opposite is true as well. So when I compare K to one, I don't buy K. Okay. So now I have this binary choice. I look at two products. Yes, I purchase product one. No, I don't purchase product K. Okay. Or no, I don't purchase product two. So I have this binary choice model, and that's again why this is basically a support vector machine. Yeah, so that's just what I just mentioned. So you have this binary choice when comparing two products, 1 and k, and you have a yes, no decision. Yes, I choose 1 over k. No, I don't choose k over 1. So basically, the utility function, this weight vector W, can be learned by this optimization model, this convex optimization model, which is very, very similar to this to the SVM model of Vatnik in 1998. And the main difference is just the set of features. What is a feature that I have in my data? The feature is not the feature of the products. The features are basically the differences among two different products. Any questions about this? Because that's the core of the model. So this is just what has been already introduced in the literature.
Last one question here. So the W here is referring to what exactly? So because it looks like this one is the main variable that is going to be minimized.
Yeah.
But how it work in the preference learning area? Yeah.
So this W is basically the weight of the feature. That's what the consumer, how the consumer weighs a feature. So x1t minus xkt gives me the difference between two products. Let's just take as an example the camera, again, camera quality. Let's say I have a product that is strictly one feature, just the camera quality. One is 40 megapixel, the other one is 15 megapixel, okay? So I have a difference of 25 megapixels. So the weight W is how much the consumer will put a weight on each of these megapixel difference, okay? So if this weight is 10, let's say an additional megapixel difference will drive the utility by 10 units. Okay, so it's just a weight for each unit of that feature, whatever that feature describes, or whatever that unit describes.
Mm-hmm. Thank you.
Yeah, so that's the model that has been introduced in the literature. So this set of papers by Avenue and his colleagues, and Curry and Shui and their colleagues. So set of literature that has appeared following the introduction of these models. And a lot, I mean, most of the literature on this has appeared in marketing type journals. So a lot of this is happening in the marketing literature, in fact. However, there is a big problem in these types of problems. They assume that the customers are, or the consumers are really rational. So they, when they are picking choice 1 over choice k, well, actually, they value the utility of choice 1 more than the utility of choice k. That's what I started at the beginning by saying, well, I have this strong assumption that I pick the highest utility. So there is an assumption that the consumers are rational. Well, in reality, consumers are not rational. Consumers are actually irrational. And there is a lot of evidence in the literature, and of course in consumer behavior, is that consumers are irrational. For instance, consumers choose health insurance plans that often cost them a lot more money than they need. So, I mean, sometimes well, and for many cases, actually, you don't need all the things that are offered in an insurance plan, and you often pay for an insurance plan that costs more, although provides coverage that you don't actually need. And it's not really a lack of information. The information is there, but consumers, as I start by saying, are irrational. So they don't really pick the best choice in terms of utility in practice. Again, like another example is also from the consumer behavior literature, is it's very common that you pick a cell phone plan that doesn't really match what you need. And you pay a lot more for this than you would pay if you were able to pick the best cell phone plan. Also, like many of us would probably pick a branded drug over, for instance, other ones that would be cheaper but still have the same dosage, same ingredients. And again, this is all coming from consumer behavior literature. And this becomes a bigger problem when you are faced by complex choice, or you are forced to choose promptly, or the time is restricted for you to pick the choice, which is the case for most of our consumer purchases. So in fact, this assumption of rationality that comes from utility maximization is not really true in practice. So it's a problem, of course, for these models, because, well, this assumption that the consumer choices are correct, which drives the models, doesn't hold true. For instance, a complex choice is, like just one example of complex choice, we have two smart thermostats. They're both exactly the same price, different features, different shapes. They all do the same thing in the sense that they are a smart thermostat. But of course, they have different features, and picking one of these is actually not that trivial. So which one is the best one to pick? And if there was one best choice, well, only one of them would exist in the market, not both. But there is no obvious one best choice. And the reason I'm showing this example, because I mean, that was very common for us. So at some point over the past few years, so we were offered these smart thermostats from the government, and we had three choices. I will show them in the next slide as well. And you had to pick one, and whoever you talk to, like they will tell you, well, I picked this one, and someone else will pick this one, and they are all the same. Like they are offered to you for free, basically, and then you need to pick one of them. And there wasn't a uniform decision which one is the better quality. So in fact, it's very hard to make a decision that maximizes utility as a consumer. And why is it hard? Like, again, looking at the consumer behavior literature, so it's, although all the data is available to you, so it's not really lack of data, so you exactly see the product. However, the way you perceive these attributes may not be accurate. So the way you read these attributes, the way you perceive it, or the way you value them may not be really accurate. And even harder when you are actually comparing. It might be easier if you're making the decision that I purchase this product or not, but in fact, you are offered a comparison, and it becomes very hard to compare these alternatives, so, or to perceive these differences in these alternatives. From a model perspective, so the way we can model this idea that it's very hard to compare, or we actually cannot accurately perceive the product, is by saying there is an error in what we perceive. So actually, the actual product feature is X bar, but in reality, what the consumer sees is X bar plus some error. So the way I perceive it as a consumer, there is always an error. And in fact, actually, I'm not really looking at one product at a time. I'm actually doing a comparison. So there is an error, this E prime, there is an error E prime to what I perceive as the difference. So when I'm looking at the difference between these two thermostats, I cannot accurately say what is the difference. So I'm looking at 2.08 inch screen versus 3.5 inch screen. There could be some error in what is that difference. Or I'm looking at the resolution, 480 by 480 compared to 320 by 480. So there is an error in what I perceive as the difference between these features. So in fact, the data that I have is not the accurate measure. So the data that I have about the difference at each choice occasion, the ZKT is the difference in the product features plus some error. And I'm always picking choice one. So I'm always picking, I have an error when I'm comparing choice one over the rest of the choices that I have. So now when I'm finding this maximum margin hyperplane, I'm doing this maximum margin hyperplane optimization while this error exists in the model. So I have this epsilon error in the feature. So I have the correct features, which are Z bar, plus some error due to my perception. So when it comes to the model or the optimization model, well, it's true that there is some error in what consumers purchase, but I think it's safe to say, well, this error is bounded. So it's not that there is an infinite error. So it's not that I look at the difference between the features and the error is infinite. So there is always a bound on these. There could be a bound. So it's reasonable to say there is a bound on this error. And the way we enforce it is by saying, well, looking at the norm of the error vector, there is a bound on that error. Well, if the error is infinite, I mean, the data basically doesn't offer you anything to learn. So there is something, some bound on that error itself. Now then I have, I'm trying to find a utility vector W such that I'm making this choice that is 1 over k, but I want this error to sort of be as minimal. So, or this error, when I multiply it by the weight of the utility, to be as minimal as possible. So in some sense, I'm saying, well, I want to come up with a utility vector, a preference learning model, such that I know there is some error in there, but when I look at the cumulative error in this utility vector, it should be as minimal as possible. So I would like to minimize this weight W multiplied by the errors that exist, knowing that the errors are bounded by a certain bound. And there is a closed form for that optimization problem where this dot product has a certain value. So in fact, I can rewrite my optimization model with this additional term, which offers me some slack, basically, where that accounts for the bounded errors to offer more robustness. So this is a robust optimization model of what was presented earlier in the literature. So what we're doing here is actually adding some robustness, some form of robustness to the model, and that offers us a higher accuracy. So that's the first new thing that we have, sort of extending these original models and adding more robustness to them. The other thing that happens when it comes to consumer choices, well, consumers actually don't retain the same decision over time. So if I'm showing the same products to a consumer repeatedly, of course, we're talking about an uncontrolled environment. We're talking about in reality, in practice. They are looking at the same choices, and you show them today and in 6 months and in a year. It's not uncommon that people change their mind, but nothing has changed in the product. So why do people change their mind? That's because, I mean, the consumers are irrational and at some points might have made the wrong choice at a certain point in time. So the choices are not consistent, which was a very strong assumption in earlier models. It says, well, the choices are always consistent. On top of this, choices in reality violate transitivity. So if I pick choice 1 over 2, then 2 over 3, sometimes if you show 1 and 3 to the consumer, they still would pick 3 over 1, which doesn't make a whole lot of sense. If you prefer 1 over 2 and 2 over 3, why do you flip your choice when you show products 1 and 3? And this is not uncommon in reality. So transitivity is violated in reality. So the assumption that consistency and transitivity are actually impractical when it comes to human behavior, and there is lots of evidence from consumer behavior coming in. So even in controlled environment, this is not true. So in uncontrolled environment, it's even worse. So again, you have these 3 choices of thermostats, which we were actually offered. And as I said, it definitely wasn't uniform what was the better thermostat to pick. The assumption of consistency says, well, if you're picking the product, you're always maximizing the utility. So we have this argmax, so it's always you're picking the highest utility, but this is not true. So the way we sort of address this is by by saying, well, you have all these consumer choices, you have all these preferences, they are points in the Cartesian space. Just look at the centroid of all these choices, and any point that is very far from that centroid, well, it's more likely to be a wrong decision, or more likely to be an inconsistent decision. So you need to put a lower weight on it. So we actually can calculate a weight in terms of chances of the choice being correct or not. So there is a weight that gives us the probability of that choice being a correct choice or irrational choice. So we modified this model. So now if you look at the objective, there is a weight SKT that is multiplied by this error. So there is a weight for that error that we add, which is impacted by the probability of the choice being correct or not. So the points that are very close to the centroid are more likely to be correct choices by the consumer. So we put more weight for that error that we're trying to optimize and less weight otherwise. So this adds a lot more robustness to the models. Well, this is the model. So that the final, at least first stage model that I'm showing here. You see there is a norm in the objective, there is a norm in the constraint. So things can be linearized if you have this Q norm. So if you assume this norm is an L1 norm, you can linearize it. If it's an L2 norm, this is second order cone program. If it is an infinity norm, or again, this can be linearized. So we have a model that we can actually solve quite quickly as an optimization model. So there is no issues in terms of numerical solvability of the models that we're developing here. In terms of some results, I'm not spend a whole lot of time on this. We just want to say that we do a simulation design type experiments. So this is, we copy exactly the same experiments that have been done previously in the literature. So we don't really design the simulation. So this is coming from the previous publications that we have, and we're just comparing the results in terms of different levels of errors that are introduced. So when I talk about no noise, this is when there is no error. So we assume everything is perfect, the data is perfect, there are no errors introduced. So, and then we introduce some low error. And we have two types of error, as I said, one in terms of perception, the other choice in terms of consistency. We have a different variation, low and high from this. From the results, so to summarize these results, when there is no error, of course, when we introduce robustness, it doesn't pay off. Actually, we perform worse, which is expected because, well, the data is perfect, there is no error in there, so sort of the models that don't have robustness are always the better. So we have roughly 82% accuracy for that model that has been introduced before us in the literature. However, as soon as we start introducing some levels of errors in the choice or inconsistencies on the choice, the results start changing. So now we have these robust models that start performing better. So particularly we have this, the model with, we have the infinity norm, and there are reasons why the infinity norm would perform better that we're trying to explore, these models start offering more accuracy in there. We have the same experiments again on a set of real data, again doing the same type of results, showing that we obtain higher accuracy when we introduce some robustness in the models in the presence of error. I will take the last few minutes to talk a little bit about the main thing that actually drove this research, looking sort of at the privacy preserving aspect of it. So that's where I would like to conclude. And there is a lot of talk about fairness in there and favoritism in there, and that's quite controversial when it comes to preference learning, because you're actually favoring in there, you're segmenting markets, you're creating something targeted. So you're trying to differentiate between people, you're trying to differentiate between markets, and that's quite controversial in there. So that's, I mean, depending how you read this, but actually it's some discriminatory, some discrimination in different places. So different markets are offered different things, and in some sense there is some discrimination between the different markets. And there is a lot of talk that when it comes to creating models that try to discriminate, the outcomes are not really great, and there is again lots of evidence in the literature, at least in the last few years, talking about the bias when we create such models. And besides sort of the fairness, although we'd like to keep the models fair, but segmentation is needed. That's really what drives profits. That's really what sort of the retailers, manufacturers demand today. And when it comes to segmentation, so again, there is some literature talking about this. Anyone would think about sort of segmenting based on profiling consumers. But the problem in there, so sort of the characteristic that identifies a consumer, for instance, their demographics, are actually not what drives their behaviors in terms of purchasing decisions. So the traditional way of segmenting consumers based on demographics, when it comes to reality, actually doesn't work. And that's what creates all the biases, a lot of the problems that we're seeing in the discriminatory type of analytics, because we're doing segmentation based on demographics. So we'd really like to avoid, or we don't want to do segmentation based on demographics. And there is ample evidence about this sort of segmentation. I mean, different products, different markets are offered differently. So even the Starbucks coffee in different markets is different. So there is this nice article looking at the difference of Starbucks coffee in the UK and the US, and it's a lot different in terms of products that are being offered to different markets. And this could be, of course, looked at as a discriminatory type of analytics, particularly if it's driven by consumer profiling or consumer demographics. What we do in here is that, well, we say, well, we don't want to do any segmentation based on consumer demographics. We purely would like to learn segmentation based on their choices. So there is nothing about their consumer demographics. So we'll say, well, actually the market is not uniform. So we cannot assume that there is a single utility function for all this market. In fact, we have D different utility functions. We have D different markets. And we'd like to learn these D different markets. So instead of a single utility function, now we have D utility functions. So we have this vector WD, and each choice belongs to a segment. So we have actually a binary variable that tells you which choice belongs to which market. And each choice should be assigned to a single market. So there is nothing about their consumer profile. There is nothing about their consumer demographics. So you can change basically the model that I introduced before by introducing this degree of freedom by saying, well, now we have the different utility functions. Consumer choices should be assigned to a market, and that's the final model that we have. So creating segmentation without introducing or without the need of any demographic data. It's purely on choice data. And we wanted to see how that performs. And the way we test this is by comparing this segmentation to sort of different ways of doing segmentation. Let's say full information. Full information, I know exactly the segments and try to learn it. So that's the best case scenario. So the first line of results is the performance of our model. The second line of results is the perfect information. That's the best we can do. The naive way is by saying, well, everyone is the same. So there is a single market. So that's the accuracy of the model. Random is by assigning people to different segments randomly. So, and clustering is by doing clustering in terms of consumer choices. So K means clustering, basically. What we see here is that, well, of course, the full information is the better one. That's the best case scenario. By introducing this degree of freedom, we are able to learn consumer and segmentation. So we have higher accuracy than, of course, assuming the naive way by saying all the market is uniform. Everyone is the same single utility function. So that's the most important part that we wanted to see, is that it's better to do segmentation than assuming everyone the same, indicating that people behave differently in different markets. Of course, random, I mean, you wouldn't do it in reality, but even worse, like if you do k-means clustering on the data and try to learn based on each cluster on its own, it really performs a whole lot worse. It's quite an interesting result for us that we saw, studying a little bit of the literature, and there is some evidence in the literature that sort of clustering techniques don't really work that well. We're digging a little bit more in terms of this marketing science literature, trying to understand why doing clustering than segmentation doesn't do as good as we hope for. So that's the last result and the last model that I want to introduce, and I'll conclude in the last minute. So I hope by this stage I convince you that sort of this consumer preference learning is pervasive across in all the industries, in all the markets, and there is a lot more requirements of accuracy, customization, but there is a lot of focus on interpretability, privacy protection. That's what we're driving. So between robustness, accuracy, and privacy protection without demographic data. As you see, optimization techniques here coming, sort of the models coming from robust optimization have helped us quite a bit in improving the results. And we have quite a bit of extensions we're working on when it comes to group decision making. So now that you know utilities, what would be the best products to offer? So sort of optimal assortment planning, so that we're working on with an industry partner in there. So. Yeah, thank you for your time. And I think I can take questions if the time permits.